Hello and welcome back. We have understood support vector machine at a high level, and we understood that it's a large margin classifier. It always tries to choose the support vectors in such a way that the margin is going to be large. The decision boundary is going to be exactly at the middle of the support vectors, and the support vectors are chosen in such a way that the margin is always large. So there are two variants in SVM algorithm. One is hard margin classifier and second is soft margin classifier. Hard margin classifier always strictly imposes that there should not be any data points on the margin. There should not be any data points falling on the margin, or there should not be any data point falling on the wrong side of the decision boundary. So if you look at this diagram, this data point, this data point is yellow circle. This should be present on this side, not on that side. So if data is like this, right, you cannot do a hard margin SVM classifier. There is no way that we can do it. Either way, right, if you choose this as this as a support vector and that as support vector and try to do decision boundary, this blue rectangle, blue square is actually falling on the wrong side. If you take these two as the support vectors, the yellow circle is falling on the wrong side. So if you try to do hard margin SVM classifier, on this kind of a data, you will never be able to build a model. So always soft margin classifier is good because you can play with the hyperparameters and make the model work best on the train set and test set both. So let us see what is soft margin classifier and how to build that. Soft margin classifier is always tries to find a balance between the margin, the street, right, the space between the two support vectors as large as possible and limits the margin violation. What is limiting large margin violation? The data points may be falling on the margin on the right side of the margin or on the wrong side also. If you see this, right, if you look at this diagram, the margin is large and there are some data points falling on the margin. See this data point is falling on the margin and it fell on the wrong side. That means what? On your train set, one record is being predicted wrong. That's okay, as long as on test set also you are getting the similar kind of accuracy. So we are trying to have the margin as large as possible even when we are having some data points falling on the on the road on the margin or on the wrong side of the margin also, or on the wrong side of the decision boundary also. When the record falls on the wrong side of the decision boundary, that record is going to be predicted wrong. This is all on test set, train set, right? Once the model is built on trained on train set, it should be generalized well so that it works well on the test set also, right? So that's our goal. So in soft margin classifier, it always tries to keep a balance between margin as large as possible. It tries to do margin as large as possible, and at the same time it limits the margin violations also. It tries to keep margin violations as minimal as possible. If margin violations maximize, right, what happens? Many data points are falling on the wrong side. That means model will not work well on the train set itself. That means the model is underfitted, right? Margin violations should be controlled. Margin violations should not be maximal. At the same time, the margin should be maximal so that on test set and production, if any peculiar data points come, the decision boundary can handle it appropriately. So that is the purpose of soft margin classifier. When we see the diagrams, right, these diagrams are on train set. Okay, on train set. If something is happening here, some record is being predicted wrongly, it is on train set. On test set, most probably, even if some errors are there, it may be able to handle. The erroneous records are there, it can handle. The C is the hyperparameter which actually handles the margin violation. So, cost function and C hyperparameter will help bring balance between large margin and limiting the margin violation. So how it helps, we'll see. But if you look at this cost function, right, this cost function is yi cost 1, the class 1's cost, w transpose x plus b, and yi 1 minus yi cost w transpose x plus b, the cost of 0. If you look at this cost function and the additional regularization parameter, regularization term, and if you look at this cost function, this is actually logistic regression's cost function. They look similar, right? But the hyperparameter, the lambda hyperparameter, shrinkage parameter, is actually multiplying the regularization term on the logistic regression. But in SVM, the same, the hyperparameter is multiplying the cost function. So if you imagine that c is equal to 1 by lambda, it actually works like a logistic regression. That means in logistic regression, when you increase lambda, the overfitting reduces. When you decrease lambda, the overfitting increases. In here, in the SVM algorithm, it is opposite to that. If you increase c, the overfitting increases. If you decrease c, the overfitting decreases. The c hyperparameter is directly proportional to the overfitting. The reason behind looking at cost function and understanding mechanics is that we need to be able to play with the algorithm, because the implementation is already there. We just need to play with the algorithm and make the model the best. So what happens when you increase c? The overfitting increases. What happens when you decrease c? The overfitting decreases. That means overfitting increases means the model will work well on the train set. It fits well, right? The decision boundary and the support vectors are going to be in such a way that all the data points in train set will fall on the right side of the data, right side of the decision boundary. But when you look at the test set and when you actually try to play with the test set, right, it may not work. It may not work as exactly it is working on the train set. That is overfitting. So with the high C value, fewer margin violations on train set, but ends up with a small margin. If you see this, if C is equal to 100, the margin became so small. See that? The margin became very small. So, when the margin became very small, the margin violations reduced. See here, there is a margin violation, right? Here also there is a margin violation, but there is no margin violation here, right? The margin violation there are no data points which fell on the wrong side of the decision boundary when C is equal to 100, right? When C is equal to 100, there are no data points fell on the wrong side of the decision boundary. This solid line is the decision boundary. But this may not work well because the margin is so small that it will not allow it will not allow a small mistake also. So that may cause problem in test set. It may not work well on the test set. It may work perfectly on train set. It is actually doing 100%, giving 100% accuracy. If you look at the diagram, right, all the right points are on the right side, right? All the the snuff points on the top and all the light blue points are on the bottom. That means it is giving 100% accuracy here. But on test set, there is no guarantee because the margin is so small. Okay. So when C is high, the margin becomes so small and the model may overfit. But when C is reduced, right? When C is reducing, right, margin size is increasing. See this? With C10, size increased. With C1, the size even increased, right? When I say the size is increasing, the angle also a bit changes. The angle of the decision boundary also changes a little bit. Because of the change in the angle, the data point actually fall on the right side here. You see, if you make the C hyperparameter 100, the angle changed a little bit. That's where the data point fell on the right side of the decision boundary. Here with C is equal to 1, the angle is actually moving like that, upward. See this? It moved a little upward, so this data point came close. It is moving even farther, right? The data point is like the support vector, the decision boundaries angle will change a little bit. When you are using SVM, based on support vectors, the direction, decision boundaries angle will change. That's the difference between the SVM and logistic regression. In logistic regression, there is no way to play with the decision boundary. You will get the best thetas, and you may actually play with those shrinkage parameter to adjust the the curves, make the curve smoother or maybe complex, but you cannot actually play like this. That's the advantage with the SVM algorithm. If the C value is small, the margin becomes big, margin becomes large, and may get into underfitted model also. When margin becomes too large and margin violations become too big, the model may not work well on the train set itself. That is not good. So you need to play with the C hyperparameter and find the best C where exactly the model fits. The next point, the support vector machine is sensitive to feature scaling. When the features are scaled and are on this are on similar scale, the model works well. If you look at these two diagrams, the width on y-axis I have taken, and length is the length I have taken on x-axis. These two are two features based on which we are trying to make predictions. So both are at c is equal to 0.5 only. I said when you change c, the angle will change, right? We are not touching this hyperparameter c. Okay, we have taken the raw data and tried to build a SVM model and try to visualize it. When I try to visualize it, the decision boundary is like this, and the support vectors are so very close to the decision boundary. The margin is so small, right? This may overfit, right? This is actually kind of overfitting scenario. So when you do the feature scaling, right, I changed the width also. I actually applied feature scaling on width also and length also. Then you see the decision boundary is so clear, right? The left graph, unscaled data, shows overfitted small margin versus right graph, scaled data shows large margin. This is for the same C is equal to 0.5 hyperparameter. So when you are applying SVM, you need to make sure that the data is scaled. Always the data is scaled. When data is scaled, the algorithm performs well, and you can play with the hyperparameter C and make the model even better. Okay, so that is the sensitivity related to the feature scaling. In next session, we will look at exercise or coding example using SVM on iris dataset. Thank you.